Okay, so we start with week eight's tutorial session. So before beginning, I think I should answer the question that was brought up last week. So last week, there was a question uh, that when I'm doing a lambda, and when I'm computing the lambda return, then the highest weightage is given to my one-step return as compared to any other return. So is it true or false? Okay. Uh, so I'll just write down the expression for, okay, I'll just write down the expression for the, cool. So this is how the expression for your expected return looks like when you're trying to compute your lambda return, right? So the question is, does the one-step return get highest weightage compared to any other thing? Okay, and uh, if you just look at one example case, let's say you have an episode of length 3, and let's say your lambda is point 7, and your episode has a length of 3, right? So you think of it in the following way. So you have for the first two time steps, you're taking into account the one step and the two-step return. But after that, for subsequent increase in the n step return, when n increases beyond L, then you just use the complete Monte Carlo return, right? So my one step return has a weightage of 1 minus lambda. My two step return has a weightage of 1 minus lambda times lambda, and so on. While my NC return has the weight of this quantity, right? So if my lambda is zero point 0.7, so my one step return.
Manav, the screen is not reflecting what you have played.
Okay, okay.
Yeah, it's visible now.
So it's visible now. Okay,
Yeah, yeah.
okay, cool.
Yes.
Right. Uh, so for my one step return, my weightage is 0.3. For my two step return, my weightage will become zero point 0.3 times 0.7, which is 0.21. And this thing would be just the remaining of whatever is left, right? So this is 1 minus 0.3 minus 0.21, which is 0.49, right?
Yeah.
So you see what's happening here is, uh, let me draw the plot again. So if this is my weightage, so this is 1 minus lambda, this is my weight. So this falls like this, right? So if I were to divide this into three partitions, so the first partition would be for the one step return, the second partition is for the two step return, and the third partition would be for the MC return. So what you're looking at for calculating the weight is not the height of the y-axis, right? What you're looking really is the area under the curve.
Right. Yeah.
The area, the region which has the maximum area would have the highest. That's the reason why when you have really small episode lengths, so your Monte Carlo return typically gets more and more weightage, because after you have done one, after you have taken two steps, let's say you are at time t equal to 0, you only take into account the one step and the two-step return. When you're at time t equal to 1, you only take into account the two-step return. And after that, all you have is the Monte Carlo return. So naturally, the maximum weightage will go to the M return as compared to the one-step return. Okay.
Okay.
Okay. So I hope this is clear. I'll just erase everything quickly.
Well, maybe let's keep that way. It'll be
Okay.
useful when we're referring it
Oh,
later.
okay. I'll write it in a later slide later on. Okay. I'll write it in a proper way.
Sure, sure, sure.
Okay. I'll just get with this. Okay. So the main motto today is to just do a quick recap of what has been covered in week 8 lectures, and mainly it has to deal with function approximations, right? So earlier, what we have been studying till now is we have some access to a value function table, right? So you have a value function table to which you can quickly refer and get the corresponding value. And that value function table is what you keep on updating. So the representation that you have is a tabular representation. So you have something called as a lookup table, and you keep accessing that, or you keep querying that whenever you need to evaluate your policies, right? So the main drawbacks this issue, uh, sorry, the main yeah, it's fine. The main drawback this method brings up is that first drawback is that it takes up memory, right? So there are it is memory intensive, because if I have millions of states and millions of actions, then I would need uh, a lookup table which is S cross A. So it's a million cross million size matrix which I need to maintain. And after maintaining that, so if I have millions of states and actions, I would require a large matrix. Second thing is that this notation only works whenever I have some discrete action space or discrete state space, right? If I have a continuous state space, then there is no notion of a tabular based method, because the action space is continuous, the state space is continuous. So the tabular grid notation like doesn't make sense here. So one of the drawback is it can't handle continuous spaces, right? And even more important is that if I have a million cross million matrix, I would like to visit each element in that matrix a sufficient number of times so that I can get a good enough estimate of what is happening, right? If I don't visit each state a sufficient number of times, then the the estimation of the value function that I have would be faulty. Okay, so that's why this doesn't generalize well, since if I have a million cross million time size matrix, I would like to visit each state at least some few thousand number of times. Okay, so uh, that also adds up to the computation, right? So one like another way to look at these stuff is something which we'll refer to as a parameterized representation for the lookup tables. So instead of having a lookup table, we would like to have some parameter from which we can estimate whatever value functions we have given the inputs, which is the states or the actions, right? So my v of pi, I would like to estimate it as a function of some parameters theta, right? This gives me 2 points. First is that in order to do this, I should have basically a dependence of parameters on the output. So whatever parameters that I have, they should have some linear dependence with respect to the output. And second is that once I have some estimation, I need to have some error metric or an error measure in order to evaluate like how close my parameterized estimation is with respect to my original v pi, right? So I need these two values. So this thing, okay, we can probably like uh, look at it, since we if we have some linearized representation of, or some linear representation of the parameter theta, we can always show that and also the parameters are linearly independent, we can show that the output has a dependence on the parameters. But for the error measure, we would like to discuss in details what could be the different error measures that people use, right? So one common method that a lot of people use in machine learning literature also is known as the mean squared error. Turns out for your classical regression problems or even your ML regression problems, the mean squared error estimation works really well to in your convergence, right? So the mean squared error equation is written as such. So it's 1 over n times. So this is my summation goes from s to 1. So if I have n states, no, yeah. So this is my mean squared error. This is my mean squared error notation. But here, what it does is it inherently assumes that each uh, state's sample that I draw will contribute equally when I'm computing the average or when I'm computing the mean over all the least squared errors, right? So the change here looks like should be something like, so I remove the 1 by n term. I don't want to give an equal weightage to all the terms uh, in the mean squared computation. Instead, I give some weighted representation for this for each term that I'm using when I'm computing the final mean, right? So this extra term that I've added, this term here, is known as the steady state probability distribution. So what the steady state probability distribution does is that it maintains some estimate of the states that you're visiting more often than the others. And based on that, the probability distribution of that corresponding state varies. And it turns out that more number of times I visit a particular state S, my steady state, the value, like the probability for that state would be higher, or the weightage for that state would be higher, and I would like to include that in my mean squared error computation, right? And now the question is, I have introduced a new term. Now the question is, how do I estimate this d pi of s? So the way to do that is uh, by using online sampling. Okay, other no, not online. This is on policy. This is an on policy sampling. By using an on policy sampling method, I can basically estimate my d pi. So the way it works is, since I'm doing an on policy sampling, so my MSE can now be represented as, rather approximated as, is 1 by n. Okay, so this is again similar to what we have been doing on what we had been looking at in our TD learning methods or in your stochastic approximation method. So this particular thing is known as the target here, and this is the current estimate. Okay, so at each time step, I am taking the difference between the target and the current estimate, and I'm like using stochastic averaging to update my mean squared error, right? So this is what is happening. But one big issue here is that my target is unknown. in your machine learning problems, in your classical regression problems, you have access to a target, which is a known annotated data set, right? You have a data set to which you want to fit the input to. You have some fixed output labels, right? So so what happens in regression is, okay, I've written it anyway. Yeah. So what happens in regression is you have some f of x and f of x, and you want to approximate some function that models this sort of behavior, right? Yeah. So same thing that I've written. In regression, you typically have access to your x and f of x, based on which you're trying to approximate a function uh, f hat of x. But in reinforcement learning, instead of the x and fx data, you have access to a trajectories that you have followed, right? If you're doing an on policy sampling, you have access to a trajectory. So the trajectory looks like this. You have S0, A0, R1, S1, A1, R2, and so on till you reach the terminal state. And from that trajectory, what I'm trying to do is I'm trying to estimate my V hat. Okay. So I want to represent this RL data, this RL information that I have in terms of my regression, in terms of my regression data, right? So the way you do that is you have your state, and then you have your corresponding, and so on, right? So what do you call this term? This term is nothing but my expect return, right? This term is my expected. This is my expected or rather the complete return, right? This is the complete return. But unless you're doing a Monte Carlo, you don't have access to the complete return, right? So instead, what you do is you use some sort of bootstrapping method. So in bootstrapping, what you do is you only look at the reward in the next time step, and after that, you use your value function estimate for state st of one, and correspondingly, you develop your data like this. Okay, so this is the data I have. So once I have the data that I wanted to represent in terms of my regression problem, then I shouldn't have any issue, right? When I want to estimate, if I want to estimate this quantity over here. So what do you think could be the problem when I'm trying to estimate? Okay, I think my screen froze.
Yeah.
Okay. Okay. Yeah. Uh, I think it's visible, right?
Yes, yes, that's it.
Yeah. So I have represented whatever data I had in terms of what I typically do in my regression problem. And now I want to estimate this quantity over here, right? So how do we, like, what do you think would be the issue? I have the data. I can use my regression and uh, estimate my V hat, right? What do you think could be the issue here? Okay, I'll tell you. So the issue here is that the target that I have. So this is my input and this is my target. Okay. So the target that I have, this is not the actual target, but this is some sort of a bootstrap target, right? So this is a bootstrap target. And the way I like write this bootstrap target is that I'm using an estimate of whatever value function that I have till time at time t plus one, or rather I'm using an estimate of the value function that I have to predict my v hat of s, right? So I'm using an estimate of v hat to predict my v hat. So you see the issue what comes up here. So the target that I have is always non-stationary, because any update that I make to my theta would eventually end up updating my v hat, because v hat is parameterized by my theta. And for every theta update that I have, my v hat changes and my target changes. So the target that I have is not stationary. The target is continuously moving, right? So this is one issue when I'm trying to do function approximation. So that's why I can't directly do a regression once I've represented the data over here, because I don't have access to the complete target. I only have access to the bootstrap data. And eventually, my theta update looks something like this. So my theta t plus 1 is theta t plus alpha. This thing. This is the target. V dash t plus 1 parameterized by theta t time t minus v hat st parameterized by theta at time t, the whole square. Okay. So this is how my theta update looks like. Now, I have some approximation for the function that I have, but now I need to look at a way on how to solve this if I have a non-stationary target, right? So one method to solve this problem is known as linear parameterization. So the idea is simple. What I do is I start with state s, and then I encode it to some basis function phi. So this phi basis function is of this is a vector of length k, and this encoding is actually something that is some sort of an art or intuition or heuristic. Or even better, if you move to deep RL, this encoding is something that you don't need to care about, because your neural networks takes care of such encoding. So just to give you an intuition what this encoding is, let's say I have a grid world uh, example. Okay, so let's say my agent is here. Okay, so one way of encoding this is that the agent's current position in the state, right? So let's say the agent is in row 2 and column 2. Okay, so my encoding is the row data and the column data. This is one possible encoding representation. Second thing is, again, let's say my agent is here. I'm trying to only find out where obstacles are present in the vicinity of the agent. So if the agent can only move left, right, up, down, I want to know, like, at each direction, what the is an obstacle present, or obstacle is not present. Okay. So if I were to move it clockwise, there is no obstacle in the up direction, one obstacle in the east direction, one obstacle in the down direction, and no obstacle in the west direction. Okay, so that is another way of encoding the state. And one more method that you can look at is, let's say again my agent is somewhere here in the environment, and it needs to go to the goal, right? So one thing you can look at is I want to know what is the bearing, or what is the direction that I need to take in order to reach my goal state, right? So if the agent is here, the goal is to the southwest of the agent, right? So the agent should know that it should move in the southwest direction to reach the goal state. Now, of course, you don't write it in words like this is southwest. Uh, so you have 8 directions, right? So you have encode it, you know. Sorry, I should put one. Okay, so this is one sort of encoding that you can do. And once you have this encoded this thing into some basis function, which is phi, so all you need to do is my value function now simply looks like theta transpose phi of s. Okay, so I'm just taking, you know, once I've transformed it to a basis function, I'm just taking a linear, uh, what do I call? This is a linear, uh, mm, what typically what happens in your linear regression? Okay, I think my screen is frozen again. Yeah. So this is similar to what you do in your linear regression thing. So uh, my linear parameterization is similar to what happens in that thing. So now, once I have this, okay, uh, so this is how my theta update will look like earlier when I was trying to do my theta update, when I was trying to parameterize my value function based on theta. So the theta update looks like this. So since now I have a linear parameterized representation of my value function, so the linear parameterized value function looks like this. Okay, so I just need to substitute this right in this part. Now, okay, there is one slight trick that these guys do. So this is the target part, right? So they magically assume that the gradient doesn't operate on the target, okay, but it directly operates on the current estimate. The reason they do this is because if you operate the gradient on the target itself, because the target is dependent on v of on v hat, so this leads to a high variance when I'm trying to compute the error function, and this leads to a very slow convergence. So the basic idea here is that you don't update the target often. Like the target update happens less often than the updates that you do on the current estimate, so that you maintain some stationarity in this non-stationary target chasing problem, right? So if you want to maintain some notion of stationarity, so the updates on target is much less infrequent as compared to the updates on the current estimate, right? So once you do that, I just substitute this. So my theta update. So instead of the gradient, uh, I have the target times my phi of s. Right? You guys can still hear me, right?
Yes, ma'am.
Oh, okay. Okay. So this is how the theta looks like after I've done a linear parameterization. Notice uh, this can be compactly written as alpha delta t times phi of s. So here, this delta t is nothing but the TD error, right? So this is linear parameterization in short. Next up, you have something known as state aggregation. So let's say you have access to millions and millions of states. So instead of updating each states one by one,
Before we move on to state aggregation, can we recover a policy pi from theta and the feature vector?
what is the feature vector? So the feature vector is
The
this, right?
phi, yeah,
Phi. Huh. So you want to recover a policy.
yeah,
So, right. So you can correspondingly compute your uh, q hat as a theta, correct?
yeah, yeah.
And your pi of t is your argmax of A.
Yes. So you're not audible.
Hello,
Yeah,
can you
yeah,
hear me?
yeah, yeah.
Okay. So yeah, you can recover your. In fact, we'll look at the control aspect the later
Okay,
slides.
okay, okay, okay.
Okay. So a state aggregation method is, let's say you have a continuous states. Now all you want to do is you would like to basically club the nearby states together so that whenever you want to update one particular state, so all the states that are clubbed in that region is updated as well. So the clubbing looks like this. So you make some circles. So this is a continuous state space, and I'm assuming the similarity is like if the states are closer to each other, then they are similar with to each other, right? Now you see, if I've done some sort of a clubbing, it still doesn't cover the entire state space, right? There are still spaces remaining. So I do more such clubbing. Okay, notice how this method leads to multiple overlaps. That's how this overlap is fine because each overlap indicates that a particular state will get updated uh, depending on the number of time the blocks get overlapped. Okay, and more the state update is better because I would converge faster to the optimal solution, right? So this method is known as coarse coding. And the way you do coarse coding is again, dependent on domain knowledge, some intuition or heuristic based method, right? So this is how your coarse coding works. Similarly, you have something known as tile coding. Okay, so the tile coding looks similar to coarse coding, but instead of drawing circles, I'm drawing tiles. Okay, so if this black square, if you can see the black square here, this black square here is the set of all my continuous state space. So I draw tiles. Okay, so I make some grid world. So first I put the green grid world, so I get some tile representation, and then I put a yellow grid, and then I get some other tile representation. So if I put more and more such grids, I get a higher number of overlaps. Okay, and more the number of overlaps, it's better. And also you need to do a trade-off. You can't just draw out infinitely many tiles, right? So it turns out like around 10 to 15 tiles gives very good results in this case. So this is how your state aggregation method looks like. So let's say you have a state. Let's say there's its application for a robot, right? In real world, it has to go from not state. It has to go from, let's say, point from some start location to a goal location, right? So let's say this is my start location. Okay, I think screen froze again. Okay, just maybe wait for a few seconds. Okay, so for let's say a robotic application, you want to move from let's say this start position to the goal position. So here it would make sense that I start off by drawing frontiers, right? So each frontier that I draw can be, aggregated or can be coalesced into forming some sort of a state aggregation method, because all the states in these frontiers that I have drawn, they have the same value function, right? So because I can do that, I can have some sort of a negative, a downward slope, so that if my agent starts here, there is some sort of a downward slope that the value function makes so that it goes down till it reaches the goal, right? So this happens in a continuous space if there are no obstacles. Now let's say I introduce some obstacle or some sort of a wall in this part. So suddenly this problem becomes quite challenging, right? You can't like draw this kind of a frontier method because if the agent is at uh, this particular position, so if the agent is at point A, it would have a very high, you know, it would have a like it will get less reward as compared to if the agent is at position B. So even though in the earlier case they were a part of the same frontier, here it would be different, right? So the way people deal with this is like they transform the space that you have. So this is a Cartesian space, so they transform it into some higher order space. So you basically draw out your room, something like this. Okay. So what you've done is you have split the wall wide open and you have made it into two rooms. And now if you want to go to the goal location, now I think the frontier, this thing makes sense. Right? So this thing gets ignored, right? So the frontier is drawn in this manner. Okay. So you have some transformed space that you're looking at when you're trying to do go to goal. So this is state aggregation method. Next up, since we have discussed the function approximation, we look at the general a way to generalize it by means of eligibility traces. So, so this is the KD error definition. So, if I were to look at eligibility traces, let me just okay. Okay, so if I were to look at its corresponding eligibility trace, so it should look like this. Plus, I'm also taking into account the gradient of the value function that I'm dealing with. Okay, so here the eligibility trace, instead of keeping track of the time of visit between the states in the past, it is keeping a track of the gradient, right? And this is how eligibility trace works. So this is for accumulating traces. And then once you have that, my theta updates suddenly looks like this. So you have 40 delta t et, right? So vector. So this is how the theta update looks like for eligibility traces, right? Next up, we come to the control aspect of it. So for control, I use my Qt, the Q function instead of the value function, the V function. So we start with salsa lambda. So for salsa lambda, my ET definition looks similar to what I had defined earlier, but the gradient part, in the gradient part, instead of V, I take the Q function. So this is for accumulating. This is for accumulating traces. And notice that here, in this case, my the length of the eligibility trace, the norm of the eligibility trace vector is equal to the norm of the theta vector. So these two vectors are have the same length. Okay, in this case, right? Okay, the screen froze again. Maybe just 2 more seconds. Wait for 2 seconds. It'll come up. Okay. Uh, yeah. Sorry. So where was I? Okay. So imagine you have the value function v pi over here, and let's say your phi is the transform basis representation with which you are trying to represent or like learn the parameterized notation of the value function that you have. So since I have my phi, the transform basis, this belongs to R of k. This belongs to the space R of k, where k is typically much lesser than n. Okay, so n is the space in which my v pi lies, and R of n is the space in which my v pi lies, and R of k is the space in which my transform basis function lies. So since uh, so in this case, the in the 3D space, my v pi lies in the 3D space, but my phi lies in some 2D space. So if I were to estimate if I were to estimate this thing based on using the least squared errored method, so typically what I'm looking at is some uh, projection of v pi, which I'll denote as v opt. Okay, so my v hat opt is basically a projection of my v pi on my phi space, right? This is some bias. This is some sort of a bias that you can expect of because I'm trying to use some parameterized notation. Okay, so this is the v optimal, and it turns out that my v star, uh, my v hat star, my v hat star won't necessarily coincide with v optimal. Okay, I think I should change the network. It's getting stuck. You guys can see my screen correctly, right? Or is there a lag? Because I'm using the same network here. There is a big lag.
It's visible, but I don't know about lag. Can you write scribble something down?
Yeah, sometimes there is a lag, but it recovers after some time.
Okay, okay. I don't know why this is happening. I'm using the same Wi-Fi network for both the devices. But okay. So here, what you're doing is you don't have access. Like you can't get directly to your V optimal. This V optimal is sort of unreachable. So I'm happy if I reach, in some neighborhood that I can get, and I'll term this as my V hat star. The reason this happens is because this happens due to non-stationarity, right? Because the target is a moving target, it may not always converge to V optimal. So if I'm in some region close to V optimal, I'll term it as my V hat star. And this also happens because I'm not using the target, but I'm using some bootstrap target. Okay, so this is the reason why this happens. So this thing is the closest projection to V pi, right? Now, once I have that, so let's say I start with some initial estimate of V naught. Operate the I operate it with the Bellman operator. Okay, so let's say I start with some V naught here. I operate with the Bellman operator. So what I get once I operate it, I get some V1, right? Some V1 hat. So I'll call it V1 prime hat. So if I operate with the Bellman operator, so it need not necessarily be in the phi space that I have defined. It might go out of the phi space. So once it goes outside the phi space, all I need to do is I need to again project it back over here. So the projection of what I have here will be my v hat of 1. Okay. So after that, I should also apply some projection operator. So this is a combination of two operators which I am applying on it to get my v hat of sorry v hat of v1 hat. So this is what I'm using, and correspondingly I do this multiple number of times till then I can get my v hat, v2 hat, my v3 hat, and so on till I get close to my v hat star. Okay, so this is how the value iteration looks like in this case. And the data that I have here is, sorry, so the data that I have is, so I have phi1 of s, I have phi2 of s, this phi of s, this thing, comma, my v of s, right? So this is the data that I have access to, and my v of s is phi s transpose theta, right? Once I have that, turns out there's a method, if I want to, look at fixed point solution, okay, for this. So this is the fixed point equation. So once I've defined this thing, I'm just like opening this up, right? So this big term over here is the projection operator. So this comes from something known as Moore-Penrose inversion. Okay, so if you have done machine learning course, you might be familiar with it. Otherwise, you can ignore how this comes up. So there's something known as Moore-Penrose inversion technique, right? So this is how this projection operator comes up. You can, if you don't know what, just ignore it for now. And this is the Bellman operator, okay, operating on v pi, right? So so this is the representation for v hat pi, and similarly, I can write a representation for q hat pi, and my v hat, I replace it by my phi times theta pi. Okay, so this phi here is a matrix representation. Earlier, here I was doing a phi s transpose. Here phi of s is a vector representation, but when I'm writing phi of s, this is a matrix representation. So I don't need to go transpose over here, right? And once I have that, this is how the equation looks like. And then if I were to solve it for theta pi, this looks like some complicated equation. Just hello, you guys can still hear me?
Yes, ma'am.
Okay, okay. Yeah. So this is how this is the solution I get for my theta pi. So here this each sample has equal contribution. So it turns out there's a weighted version of it. So instead of giving equal contribution to each of this, I can give the weighted version for this equation looks something like this. So this is how I represent my A. This is how B is represented. I mean, this big term is what I'll call as A, and this term over here is B. So it turns out my equation for so this is the equation for theta pi, and now all I'm doing is I'm just expanding each term. So I have A, so A looks like this. I do this expansion. This is how it looks like, and I'm just multiplying this term over here so that I can take it out common. So I did that. All I'm left with is this part. So turns out this is nothing but, since I have this quantity, I can estimate my A tilde. Like if I draw L samples, I can easily estimate my A tilde as I1 to L is phi of Si times phi Si minus the whole transpose this thing. Okay. So because I have written it in this notation, so all I need to do is I need to draw multiple samples of this in an online fashion and take an average of that to get an estimate of A tilde. And similarly, if I want to do for B tilde, okay, this thing, again, I can represent it in this manner. Uh, and my B tilde representation. So if I just need to roll out the B equation, and I'll end up with some estimate. I'll end up with some complicated function that I need to estimate. So if I were to write it down, this looks like ISI times RI. Okay. So using this estimation for A tilde and B tilde to solve for your value function under a policy pi is known as LSTD. This is least square temporal difference. And if you do it for the Q function, you call it as LSTDQ, which is least square TD for Q learning, right? Uh, I think a couple more slides to go. After that, we'll end the lecture. So once you have defined your TD learning for the least square method, naturally you would like to look at the control aspect for the least square method, right? So one such method is known as LSPI, which is least square policy iteration. So the way it works is as follows. So this is how I recover the policy once I have my Q. This is how I recover the policy once I have my Q hat of pi. Okay. So this Q hat of pi can be represented as phi dot theta hat pi t, right? So this is the linear parameters represent the linear parameters estimation that I got. Okay. So once I have this, so earlier we were doing argmax over A because the action space that we had was limited, right? On the action space that we had was discrete. So what happens if the action space suddenly becomes continuous? So I can't figure out the max of A, right? Because that would mean that I'm trying to solve an optimization problem since the action space is no longer discrete, but rather a continuous space. So this would mean that I would need, for each state, I would need to solve an optimization problem in order to get the action. It turns out few scientists, what they did was they figured that instead of doing all these things, I only need to solve this up. So this is an optimization. This is an optimization problem. You can see, right? For continuous action space, this is some sort of an optimization problem for continuous A. Okay. So what people figured out is that, let's say I don't need to solve this optimization problem for all the possible states that are available, but I only solve this for some J states. Okay. So I solve the optimization problem for J such states, and I get the corresponding uh, action values. And now based on the data that I have, since I've solved the optimization problem for this correspond for the J states that I have, I use it to generalize it over my entire state space and use this action to learn my policy pi t plus 1 s. Okay. So the way you do that, once you have generated a bunch of data, so all I need to do is I just need a classifier to solve a classification problem. For finite action space. Okay.
Otherwise, I use a regressor to solve for a regression problem for continuous action spaces. Okay, and this method is known as LSPI. So all you need to do is you don't need to solve the optimization problem for all possible states that are available. You just need to solve it for some J states, and then you use either a classifier or regressor depending on the nature of the action space that you have. Okay, and this is the LSPI method. And similarly, you have a fitted queue method. So this is the last slide. So the fitted queue method works as follows. So you have an estimate of Q0 hat. Okay, you use that estimate to generate, some uh, m data points in the following format. Once you have generated these many data points, you use Q learning uh, and get a new. So basically, you're using this data to estimate the target, and then you're typically extending your Q learning to this method. So you have this bunch of data, and you use this much data to get a new estimate of your Q hat. So this we'll call as Q1. And similarly, you repeat the process. You again generate m data points. Use the target is again using the estimate of Q1 hat, and correspondingly you generate your Q2 hat and so on until you reach your Q hat star. Okay, so this method is known as the fitted Q iteration method. Okay, I think this was overall what Sir had covered in week 8, and in the next classes or in the next live interactions, we'll look at a deep RL method to do this function approximation methods instead of directly trying to use fixed point equations and all to solve the parameter, like to solve for the function approximation. We'll have look at a few deep RL methods that people have come up with. I think this field is fairly new. The first paper in deep RL came out in 2015, and after that it has expanded like crazy. There are a lot of different applications, a lot of different deep RL techniques that people have used. So current research in RL that people do is more or less deep RL. So you would find like only people working in theoretical aspect of RL make use of the classical RL that we have been covering in the classes so far. But for the current research, if you are aspiring to be, to get into a domain which requires reinforcement learning, so deep RL would be beneficial for you. So it's better to get some hands-on experience with deep RL, and that's what I'll try to do in the coming live interaction sessions. Okay, so I think with this, this would be a good time to stop.
Before we close, I have one doubt regarding the assignment.
Okay.
Week 8 question 6. So it is with respect to LSPA. So the question reads, okay, where do I post the snippet? Can I post it
No, no,
anywhere?
I opened it.
Okay, cool. So that's what we discussed right now, right? LSPA. So both the assertion and reason should be true.
Which is the question number?
6.
Question number 6.
Yeah.
Okay.
So the correct option should be A, but it's given D.
The optimization problem for some states. In case of discrete action space, we need to formulate a classification problem. So the reason is to solve the given optimization problem with linear function approximator, we need to formulate a classification problem. Well, the given problem is equivalent to solving this by action spaces. As we can't maximize it explicitly, we need to formulate a classification problem. Huh. Okay. Okay. So you're saying that both assertion and reasoning should be true based on what we have
Yeah,
discussed, right?
yeah.
Okay. Okay. I think I need to get back to you. I need to discuss this with Aniket and see.
Oh, maybe I can give you some proof regarding this. In the NPTEL website, if you go to the assignment section, it's a
Mhm.
repeat question, so you'll find it in the previous
Oh, in the
assignment.
previous run,
Yeah,
of the course, right?
yeah, yeah,
Okay, I'll take a look at it. I don't I don't think I can answer right now. I need to take a closer look. I'll get back to you next week. Okay.
yeah. Sure, sure, sure.
Okay. Cool. Any more questions?
Yeah, that's it.
Okay. All right then. Thank you. Good night. Have a nice weekend. See you next
Thank
week.
you.
Bye.